Good evening and welcome to this public lecture, which is part of a series of lectures we've been running for a while now, celebrating 50 years of computer science here at York. And we're lucky today that the talk that we'll be listening to is directly related to the vision and strategy of the Department of Computer Science, which is on the development and engineering of safe, ethical, and secure computational systems. And it's my pleasure to introduce my colleague, Poonam Yadav. Poonam completed her PhD at Imperial College London on low-powered distributed systems. After that, she joined the University of Cambridge, where she worked on a number of EPSRC and EU-funded projects. And after that, she joined the department in 2019 as part of our research group, which is addressing systems. So Poonam's current research is on the safety and security and resilience of Internet of Things and edge computing, and I'm sure she's going to tell us more about this. An exciting thing about this area is it's inherently multidisciplinary, and it covers things beyond just the technical aspects of computing and touches on notions of trust, accountability, and privacy. And today in particular, Poonam will tell us more about the security and resilience in smart environments. So Poonam, we're all yours.
Thank you so much, Ibrahim, for the introduction. I'm privileged and humbled to be here today. Good evening, everyone. Thank you so much for giving your precious time today, and I'm really excited. So let's begin. So today I'm going to talk about smart environments. And the first question comes in everybody's mind: how we define smart environments? So if you go back 30 to 40 years back, this definition of smart environment emerged, that an environment which is embedded with sensors, actuators, computation, control units, and communication devices. And this environment should provide users, the people like us, a better understanding of our environment, where we are working, where we travel, where we go to hospitals, that kind of environment. In last couple of years, the smart environment has been divided into many domain-specific environments. For example, we say smart homes, smart buildings, smart hospitals, smart agriculture and farming, and smart transport or smart grids, and so on. When we talk about smart environment, from when the first definition of this smart environment came into the picture, there were two particular goals were defined. One was that whatever we do with the smart environment, it should provide convenience to the user. It should provide a comfort. And second is, whatever we do with the smart environment, it should provide efficiency. However, in last 30 years, this definition of smart environment is changing. So if we look at our recent definition, an environment is not just an environment which is embedded with sensor, actuators, communication, and computational devices, but it also provides user a capability to understand, augment, and automate the environment using artificial intelligence and machine learning technologies. So it is doing a further step which we perceived 30 years ago. So if we look in this, as I said previously, that when we initially perceived the smart environment, there were only two goals: efficiency and comfort and convenience. But over the years, we forgot about the sustainability. If I'm looking for a convenience, if I'm looking for an efficiency, We made many decisions when we are designing these kind of system. We didn't care about what is the environmental impact of these systems which we are building have on a humanity and or in our environment or on total universe. So now, due to the climate change, greenhouse gases emissions, global warming, these are the concerns we are now more focused about. And we would like to go back and see what we should do in this smart environment, what we are designing today, what solutions we are designing today. Are they sustainable solutions? And this is one emerging direction in recent years. As a researcher, it's our responsibility we should focus on. So let's take an example of a smart environment. I will take a particular example of smart transport. So let's say, assume this is me. I am traveling to work. I'm covering a long distance. And how do I measure my convenience at that time if I'm taking a long distance? Maybe the weather is a bad weather. I say I'm convenient in making that long journey, and my convenience is 30%. Now, what next I can do? How I can improve my convenience over the time? I'd say, okay, I would like to cycle to the work. I would like cycling. It will improve my time efficiency at least. I will not take 1 hour to walk to work. I may reach in 20 seconds. It may improve my time efficiency and comfort level to say 40%. Now I moved a step further. I'd say, okay, I would like to have a manual car now, and it will give me more comfort. It will provide me more convenience, and maybe also the time efficiency, and it will go to the 50%. I go further on this step, and I would say, okay, let's go to automated car. I don't even want to change the gear. And this system then provide me around 50 to 60% of convenience and support or comfort to me. Finally, because these old systems, we realized when we were at 50, 60 that they are not sustainable solution. So we think, okay, let's improve the sustainability and let's go for electric car. Say that system is providing me, say, 65% of overall comfort and convenience. And finally, I'm still, as a user, not happy. I would like to go a step further. And I'm asking, let's go for an autonomous car, where I don't have to even do anything. I will just sit down there, and the car does all the thing, and provide me 75% of convenience. I haven't given here 100% convenience, because still maybe this convenience parameter is quite user dependent. Maybe I'm still not very confident sitting in an autonomous car, because I'm worried about my safety and security. So maybe in the future now, researchers who are working in a safety or security domain, they will try to raise this comfort level of the user from 70% to 80 to 90% in the near future. So this is an example of smart transport. And you can see we have not done this whole journey in a single day. This advancement in the technology has been happening in the last couple of decades. We are slowly moving from a normal environment to a smart environment. So if you go back in here and think about, say when we had the first time we were having this manual car, we thought that's a smart environment. If you ask our parents who in 60s and 70s, they will think, oh, now for them that was a smart environment. But the new generation like us, that smart environment has become normal. That has become standard, because we are born in this generation. We are looking and we are observing that environment as a normal environment. We don't associate what the struggle parents have gone through or our previous generation has gone through to come to that stage. maybe right now, because we are in this middle 50-60% generation, our children, our future generation, when they will come in next 20-30 years, they will feel autonomous car is a normal environment. Everything is automatically done. I'm not sure, I'm not going in that argument anymore further on this discussion that are we making ourselves in context of convenience and comfort, are we making ourselves lazy? That's a different story for other day. So similarly, if you can see, many of these smart environments could be categorized in a similar way. We have smart hospitals, we have smart farming and agriculture, we have a smart industry, we have a smart transportation, smart home, smart city. So you can see the same concept has been applied over the years, and technologies are advancing at a steady state. Now, one of the common thing I would like to explain here, what is the common thing, what is the common components or a basic components of all these smart environments? So one of the basic component, the starting component in no matter whether it's a smart hospital or is a smart home, every these components have a sensor. Those have the capability to observe their surrounding environment, whether it's a healthcare, whether it's this room, whether it's a smart transport, whether it's a smart farming. The second thing this component does is the data collection. In every environment, this is a pipeline we are talking about. Third thing is in this system is a processing. So we collect the data, we process the data, and finally, after that, we communicate this data from one point to other point. So now, in this particular example, I'm talking about processing and communication. It might be possible that in our system, there will be multiple steps where we do processing and communication. It's not necessary that only one time in this pipeline we do the communication. It could be done at different stages. Finally, once we have these communication parameters, it goes for analysis. This analysis could be done at a local server, it could be in a cloud, or it could be done remotely. And finally, what we do in this pipeline is the decision-making process. Once we make this final decision, that decision has to loop back into our sensor and actuator system. So this is a loop, basically. You start sensing, it takes some input, it processes some input, it goes to communication, it does the analysis, and it comes with some decision-making capability. What should I do at this point of time as a system? And should we switch off that light? Should we switch off, should I ask my Google Home to turn off my camera at my door right now? Those kind of actions, they come back to the same loop from decision making to the actuator in the end. So now when we look at this basic component, as already explained, this processing and communication are not done at a one stage. They could be done at a multiple stage. So my architecture or pipeline maybe look like I have a sensing, then I have a data collection, communication, processing, analysis, and decision making. Even though this pipeline looks very simple, however, in a real life, this pipeline is quite complex. Because first, we don't have a one type of sensors. There is a variety of sensors we have at the sensing level. We have a variety of data formats at the data processing stage. We have a variety of processing at when we do the computation. Should I use a Raspberry Pi for a processing? Should I use my MacBook or this computer for a processing? Or should I use just a microcontroller or a nano chip to do that processing? There are different variety of processing capabilities we have in recent years, and how we decide that, what processing we are going to use. It depends on different applications. For which application you would like to use this processing? Are you going to put this as a variable on your hand? Yes, then you need to consider the size. You need to consider power consumption. You need to consider what other communication this processing device allows you to communicate to the next stage communication device. Similarly, when we come to the communication, we have a different type of communication technologies. Should I use a wire network? Should I use a radio frequency? Even if I'm using a radio frequency, what range of radio frequency should I use to make that system? Should I use a Wi-Fi? Should I use a 5G network? There are hundreds of those questions. As a researcher, as a system designer, we make every day. Finally, is the big data and cloud computing. When you aggregate all this data in a large number of terabytes of data at one stage, at one point, you and analyze that data. And finally, you generate that decision-making capabilities. And again, as I said, this decision is again go back to the system in a reverse order till the end point. So let's take an example again. I'm here. So this time I'm taking a smart vehicle parking system, which every one of us are quite aware of. So when you go to any car park, when you are parking your car, you could see there are a number of sensors there. They detect automatically your car. When we look at the variety of sensors, different parking systems may have different variety of sensors they can use to do the same functionality. They may have radar, they may have ultrasonic sensors, they may have infrared sensors, their magnetometer, or even they can use the camera images to detect a car, that there is a car in this parking lot. Once this raw data has been generated by the sensor, it goes to the next stage, which is a processor or processing unit. This processing unit does the whole computation. So it takes the raw data and try to generate some information from this data. In this particular case, it tries to generate how many vehicles currently in this car park, where the vehicles are located, which bay they are in, how they are distributed, what are their locations are, or what is the number plates of these vehicles. These kind of a number of questions you do in a car park. Now what happens? Now after this there are two steps. Either this car parking company who is holding this whole data, it may send this data to someone else on a cloud, or it just process this whole data locally and display on the entrance of the car park that, okay, right now we have 5 vacant bays in the 5 vacant places in this car park. It's their decision, right? So when we talk about as soon as this data needed to be sent out of that local area to a cloud server or any other remote server, that point, this application becomes Internet of Things. As soon as you connect the data from a local point to the internet to reach it to the server, this whole idea is now we call it as the Internet of Things. Okay, so now this car park data has reached to we decided to opt for Internet of Things option. We connected it to a communication channel. It could be Wi-Fi, it could be 5G, whatever they use to connect it to the server. And then we do the analysis, big data analytics and cloud computing. Many companies these days, they may have their own servers. They can host their servers in their own organization, like the one York. We have some of our own servers in our IT department, whereas some of the servers are being hosted on other public cloud service infrastructure providers. For example, it could be Amazon AWS Cloud Server, it could be Microsoft Azure Server, or it could be Google Cloud. For example, many of us are using every day our Google emails and Google Drive. So what we are doing, we are using a Google Cloud for storing our old data on their servers. And then finally, we generate the actions and control. When I say we generate actions and control in this particular case, what happens is this whole information that what is happening with this car park at this point of time, this information has been fed to a large number of services. These services could be the council website, where council website shows you what is the availability in different car parks around York. Or it could be, this information could be fed and back to the different displays around the city. Or this information could be used for any other purposes by the government. So you don't know. It depends on how your service providers have the service level agreement with different parties in the system. So coming back to the York, let's talk about it. So I went today on York Council website and looked at the car parks, where we have different car parks in the York. And this is the data they generate. So this data, what they have in their website, is quite static data. And when I click on every single car park, I can only see the car park spaces, which is 920 for that particular car park. It's not a dynamically updated data set. It's a fixed value which only specifies how many maximum spaces this car park has. But I have no idea that at this point of time, whether that car park is full or vacant. That information is not provided on the council website. It means we need that kind of a service. We need that back loop. Definitely, all those car parks have sensors, but that information is not fed back to the council services, and that's what we needed. Then I went back to the Cambridge Council website, and there I can see there are a number of car parks there. But they're on their website, exactly I can see in a real time that what is the status of different car park. It clearly showed that how many percent of the car parks are full at that point of time. Now, as a part of my research, that's what we do. We look into the particular use cases that how frequently the council website should update that information, because that will be defined by my network. What is where the council website server is located, and where this car park is there, and where this car park cloud server is located. This whole information in the city is traveling. So it's this makes these interactions quite complex. And that's what kind of research we do in my research group, where we look at the trade-offs. Communication trade-offs, computing trade-offs, and overhead trade-offs. So definitely we need that kind of a thing in York. So now we come back to the network of networks. That, as I said, the pipeline which I showed is not a very simple pipeline. It is a very quite complex pipeline. Data is quite distributed. It generated at one point of time in a city at one point, but this information is used by different services in a real time. And how we make sure this whole city concept, this data sharing concept is done in a secure and a privacy preserved manner, while achieving the efficiency and certainly achieving the comfort and convenience to the users. So this is the same example with the different car park example you can see here. It might be possible from a design point of view that these three pipelines belongs to the three car parks in a city, and we are doing that analysis. Maybe these different car parks, these car parks may be owned by different entities. Maybe they don't own by the council. Maybe there are private companies who own these car parks. Then how do you integrate that information together and on the council website that everyone can see that information? What challenges that particular use case bring into the picture? So I got this small funding 2 years ago, and looking at the particular use case, that how this data negotiability works in this multi-communication network, where different services within the city are owned by different organizations. And you look, what is the automated mechanism? They come to a service level agreement that this information generated by a car park owned by me, and this is the services or information generated by the other car park owners, and they share it in a more secure and privacy preserved way, so that they will not disclose their users' private information. So that was one of the case. There's another use case. My research group was looking in this particular case study is on a smart home. So now these days, every one of us has some kind of a devices. Either we have a Google Home, Alexa, we have smart watches, and everything is connected. And that's how my home looked like. Okay. Now, how I put that my smart home on that framework which I just explained. My research particularly worked on a processing and communication part of that framework. And we are trying to see in this particular project that how we provide the more resilience to the end user. If my smartwatch is connected to a Wi-Fi and Wi-Fi doesn't work at that point of a time in the house, am I dependent on that? And literally it has happened to me once. I have connected my home with a Google Home, and lighting control now only works through a Google Home, and now Wi-Fi was not working, and literally I couldn't switch off the light because I have no control. So that's really motivated me to look into this particular use case, that what should we do in that kind of a situation, how we make sure whatever the system we are designing are resilient enough. Should we put another communication channel in our home? Yes, we have a cellular network. We could use that. And in our phone, we use that every single day without even noticing that, how my phone is smart enough that when Wi-Fi signal drop, it connects automatically to the 5G or 4G network. But it does not do automatically on a reverse order. Sometimes it does, sometimes it doesn't. So there are the policies which we define on a system level, that what is my priority? If my 5G network is too expensive, then I would like to define the policy in my phone in such a way that my phone only use cellular network data only in emergencies. Rest of the time it will use the Wi-Fi. But now if you go to your phone, if you have 50 applications like my phone I have, and then every application you are checking, you use the priority with Wi-Fi and 5G or 6G, it is too much information for the user. They don't have that much time or control. And again, that's point again come back to the convenience. This particular use case is not supporting the convenience of the user. And we need a solution which understands the user convenience and comfort level. This is the same example from the previous one, where we are prototyping that use case that allows us to do the data negotiability using a different multiple communications. So another thing I have been looking in past on a low power local area networks. So as I said, as soon as we go to the wireless area network, which means I'm connected to internet. Anything I do before this wireless area network is I'm doing local processing in my environment. What happens if I disconnect my whole network from internet? Does my devices in the home environment work as the same way they work when they were connected to internet, especially for a use case like NTP service. If you remember, if your laptop or machine is not connected to internet for a long time period, when you switch off this device again, it is not able to find out what is the correct time. That's the issue, because it is too much dependent on the services provided by the external service providers. And because your phone or laptop does not have a right value of the time, it does not allow you to do rest of the other things. So that's again a dependency you are creating. And in this particular use case, I was particularly looking how we achieve that kind of a time synchronization in a local area network without dependent on external time services. Now, the final topic in this one is we are discussing about security and privacy. As I said previously, we were not thinking about it at all, security and privacy. Our whole concept of designing this smart environment was building comfort, convenience, and efficiency in the system. But because now we started connecting everything to internet, it's the Internet of Things, we are exposing ourselves to the outside world, and that brought us to a situation where now we have to take into consideration how we make this whole ecosystem secure and not to disclose my private data to the external parties or service providers without my consent. So in this particular case, one of the area in my research we work on is analyzing what kind of a traffic is going out of my devices, out of my home. So this is literally a prototype I have put in my home, where we have a router, inbuilt our own router, which analyzes every single packet which my watch is sending out, or any other devices are sending out, and we observe that, and we filter out if this is the service or this traffic is not related to the services I'm using, I should not send this data outside without my permission. So this kind of a filtering is very simple filtering. Some of my students who are sitting here, they do this kind of a work. So if you're interested, you can connect them. Another thing is in this whole ecosystem is privacy. So if you remember correctly, when we talk about this smart parking use case, we were saying this raw data has been sent to the council website. But if that raw data has your card number plates, maybe you don't want to send your personal card number plates to the council website, because that could be linked to your personal ID. If people can find out the service, they can relocate. Oh, you were in that car park at that point of a time. It means they can somehow reverse engineer and find out your location as a person locations. So that's quite scary use case. So what we can do to prevent those kind of a thing? So what we do, instead of sending all the data for analysis on a cloud, we make a decision what kind of a data we would like to do at the edge, within that local environment. This local environment can be your home. This local environment could be the car park itself. And that's kind of a keyword we use, it's called a federated learning, so that your system still learns from your data, which is important, but it will not disclose the information more than necessary to the cloud. This is another example of cloud privacy-preserved edge computing. So this is an interesting work. I thought maybe I'll explain it a little bit further. So this use case is particularly for the security. So think about if one of the devices get attacked. It could have a ransomware. It could have been attacked by a virus. It could be attacked by a malware, because all our systems are now connected with internet. what should I do, or how I design a system which can quickly detect that your device is not behaving the way it should behave. And that's what a new term we are using. It's called a network behavior fingerprinting. So you instead of identifying the device based on its identity, you look for that device based on its network behavior. What kind of packet this device is sending outside. Previously, say, in many of the denial of service kind of attack, one kind of attack happens in IoT devices where a device initially, say, my watch tried to connect to Apple server every 15 minutes. And I have that kind of a fingerprinting. But if there is some kind of a malware attack happen, most likely it will start sending it traffic, say, every 10 seconds. If that change has been happened, that shows us that there is some error, something has gone wrong in the system, and my device is not behaving the way it used to behave previously. And we take that into the action. And this technique is not a new technique. We use our security department in the university or in a big organization. This is a very well-known strategy for detecting the abnormal behavior in the networks. When something suspicious happens, you look at the traffic which is going out of the device and see, okay, it does not look like correct. But there are different ways. For last 20, 30 years, all these administrators, security experts were using statistical methods to detect those kind of behavioral changes. But because of the emergence of machine learning and AI, now these days we train lots of our machine learning model and we feed our data to these machine learning model to see if these models can detect the abnormal behavior. So that's why this new topic again came into the picture, and there's lots of research going on in this direction. So one of the things which is very important in IoT or smart environment domain is resilience. So we can relate there are three properties of any system. One is robustness, second is resilience, and third is reliability. So if I say my system, whatever the smart environment use case I have, if that is a reliable system, it is built on two properties. One is the robustness. Robustness could be it's functionally correct. It means it does what it's saying it will does, that kind of a functionality. It's efficient. It's very hard to break. So when you design a device or a product or a protocol, anything in the system, you are trying your best to make it robust. Whereas resilience property define if something goes wrong with this device, it stopped working for any XYZ reason, how quickly this device will start working again. That defines the resilience property of a system. It's the same thing, say our IT department in the university has a very well-defined security architectures and everything. But what happens if one of the services get attacked by some of the cyber security attacks has happened, and that's let down those services. We are not able to use, say, one of the service which we use in the university. Our resilience system defines how quickly IT service will able to fix that issue and bring that service back in the time. Say, is it a 1 hour? It is 24 hours? Or it is a 48 hours? Or they don't know when they are going to fix it, and it will be back on the system. So every system in a cybersecurity context, we have to define what is the resilience of that system will be, how quickly you can fix that system. And both, there are certain measures we use to measure the robustness, and there are certain measures you can do to measure the resilience. But because it's very impossible to measure the resilience in all cases, both these terminologies combined together make a system reliable, and the reliability matrix you get dependent on these two systems. So final topic, I'm concluding with sustainability. So we talk about privacy, we talk about resiliency, we talk about security, reliability, convenience, comfort, all those kind of things. But in the end, this is a point where we have to start thinking about the sustainability. What does sustainability look like in the smart environment? Is the sustainability, is a smart environment lead us to a sustainable development goals, which are, the next week and this week there's a COP27 is happening and world leaders are coming together and talking about sustainability. That's the same question we should be asking as a researcher, as a developer, as an educator. So what we could do by monitoring wastage, how much wastage we are doing with electronic wastage, e-wastage, how we can use the renewable energy sources or power sources, how we can reduce energy consumption in our overall smart environment system, how we can embed source efficiency at different stages in the environment. Some of these things we have been doing for ages already. When we talk about the energy efficiency, we always wanted our system to be an energy efficient system. But that, now how we can make sure the overall system will not have an impact on the other systems. Because we take a decision to improve my system, that has a side effect on other people's system. So another thing which, from a research point of view, there are directions that we should be able to use the biodegradable sensors. The research community should start thinking about, in these smart environments, what should we do? How we design the same sensors, say temperature sensor in this room, could I design a temperature sensor which will have a low electronics or silicon waste that could be dissolved in the environment in the near future? What will be the efficient e-management system? What should we make? And the final thing is we should make people conscious and aware about the sustainability. This is a very important point, that we should take a conscious efforts toward reducing carbon and e-waste reduction. That's the last bit from me. Thank you so much for having me today.
Thank you, Poonam. I think now we can take questions.
Thank you, Poonam, for the interesting talk. It feels to me as though data is ever pervasive. Are there particular areas where we are currently gathering data and instrumenting systems where you think we shouldn't be? And are there areas where we should be gathering data and instrumenting systems that we're not?
Thank you for this question. There are definitely there are lots of systems which has been designed and we are gathering the data which we should not be gathering the data in. As I said, even in the smart car park example, we never give a thought that we record this car recognition system that could be linked to the thing. The main problem which comes from this one is when we look at the system at a small scale, the data which we are disclosing is not revealing the information. But when we combine that system with another system, that reveals the data, more data which we never thought will reveal as an individual system. And that's the problem. As more and more services we are combining it together, that exposing the data, and no one has that clear picture. That's the problem. Because these service providers, a part of the data is owned by one service provider, part of the data is owned by another service provider, and you now would like to derive a new service. And to be true, if you go back 5-6 years back, that's what we wanted to do. We said, okay, bring your old data, let's design new services, because this new information we can get from combining your data and my data, and it will, maybe we will able to drive something. I can give a very simple example. Say we have temperature sensor in this room, and then maybe we have a smoke sensor in this room. If you observe these data separately, it's fine. You can just see the smoke level and temperature level. But if you combine these data together, it might give you whether in the room there's a fire or not. So similar kind of a situation happens in every single case what we observe. So I forgot the other question, sorry.
At the start of the talk, you talked about cities, homes, cars, things like that. Are most of the problems you've talked about today kind of the same between all those different examples? So the smart home has the same challenges of security as the city, as the vehicular networks, etc. Or are there subtle differences between those case studies, we might call it, that lead to different research challenges?
So most of the challenges are more or less the same in every single case. That's the true. The level of security, say if it's a smart home, yes, smart home has very clear picture of when you are going to the bathroom, when you are turning the lights on. That kind of information is very pervasive and related to you. But when you go to smart city, I forgot to explain that in one of the slides. I had that in my mind, that these are not isolated use cases. They are very much overlapped. Your smart home immediately become a part of the smart city as soon as you connect your smart meter to a utility company. Because now your smart meter electricity use, fine-grained data of electricity use exactly shows at what time you're turning your lights in your home and what time you're turning off your lights. And that reveals now, you think, oh, that's as part of the smart city data, not as part of my smart home, but then they are quite overlapped and connected. So you cannot separate them quite easily. Yes, definitely, if you look at the smart city, they are bigger organizations. They have challenges in terms of scalability. There are more challenges because then big data, how you combine the data. If you have to search something, how you are going to search like a needle in a haystack, that kind of a situations.
Okay, maybe a question from me. So what you described could be characterized as a problem of many hands or many agents or many systems. And also you touched on the notion of accountability. Yeah. So we all can perceive the benefits we get from the Internet of Things, the convenience you talked about. But also things can go wrong. So darkness in your home is a problem, but you can resolve it. But other kinds of problems have to do with transport accidents or incidents in healthcare. How do we establish accountability when things go wrong, when you have so many items, agents, and characters?
This is one of the biggest problems. We are not able to resolve who you should be made responsible for if something goes wrong in your system, and nobody would like to take accountability if something goes wrong. There are some progress, specifically in terms of IoT, has been made, especially in a home environment, that if a manufacturer give you a device which you can put in your home, they have to take accountability on the data which they are sending out. And this is a new standard, comes in the networking point of view, that they have to give you this is called a MUD file, which is called manufacturer usage description. So that should give you a very clear description of, if I'm connecting this device, what data, to make this functionality, I need this set of data. They have to clearly specify that information. That standard has been come out from a technical community, but now the problem is whether regulators will enforce that standard to the manufacturers. And this now goes like more of a political side of the things of IoT and regulatory bodies and government. And so I think I think I'm able to answer your question from an accountability point of view. We could develop the solutions from a technology point of view, but whether those solutions will be adopted by the organizations, that's a different, that is at a different stage.
No, I understand. That's always the case, which is regulations and societal issues lag, and technology moves fast. But here we're talking about technology, which is moving very fast at a larger scale, and that's typically a concern, which is a key challenge that we try to address within the department. But so far, if you possibly talk to policymakers, is that they're excited about the technology and hoping for the best.
Yeah.
Okay. Any other final? Yeah. One more question.
So my question isn't exactly technical, but I was just curious as to the recyclability of electronics is quite low. And it's not just the recyclability that is the problem, it also leads to social issues because e-waste is mostly dumped in the global south. So my question is, what is the electronics sector exactly doing to tackle this problem?
So again, this question, thank you so much for asking this question. Again, this is a two-phase question. One, as an end user, what is our responsibility as a social, for a social good? What is as a moral responsibility towards the environment? What should I do? And second is towards the regulators. Should we have a kind of a mechanism, if I'm selling as a company, I'm selling you this device, it's my responsibility to take it back when you are when you finish using that, and that's how we will able to reuse that mechanism. In big devices like computers and things, it's quite easy you can develop that kind of solutions. You can enforce companies to reuse those kind of systems. My concerns about, because I work in IoT, specifically those small devices which you are embedding in the system. Say, I work with soil scientists, and we are literally making these devices, putting in a soil in the farms. It works, these devices work for a year, so they are battery powered. But when we are done with our experiments, when we are done within 10 years' time, who has the responsibility to take out every single device from the fields, which are miles and miles of long fields, and what will happen to that? And I'm pretty sure these buildings are new buildings. These buildings have a number of sensors being embedded everywhere in the concrete. What will happen to them? Those kind of questions is really concerning me, and we need a more thoughtful debate on this one, how we are going ahead with these smart environments in future.
Excellent. So thanks again, Poonam, for the exciting talk. And thanks everyone for coming. We still have one more public lecture this year, which is going to be delivered by my colleague John McDermott on safe and ethical robotics and autonomous systems in December. And I've realized I didn't introduce myself. I was busy introducing you. So I'm Ibrahim Havli. I'm the Deputy Head of the Department of Computer Science. So I do hope we'll see you and hopefully more friends in December. Until then, I wish you a nice evening. Thank you.
Thank you. I just wanted to say thank you to everyone, my collaborators, my colleagues in the department, and especially my students, my PhD, undergrad, and master's students. And I'm not here without them. I'm not here without my excellent collaborators from industries. Thank you all for supporting me here and for coming today. Thank you so much.